I sent an email with very long attachments. I don't know if you guys received it. It went through? Okay. That is the best reading basically on probabilistic graphical models that I know. Elementary in some sense, but standard. If you see pictures missing, don't start sending me, oh, you know, that page is missing. Well, that page is missing because it's missing, right? That's what happens when you download things from China. Okay, some pages are missing. I'm just kidding, but, you know, some pages don't exist actually. Okay, the author has not completed them yet, especially images and things like that. All right. So what I think I realize we're going extremely slowly, and maybe it's because I don't want the class to drop it before even the first homework is due, or something like that. Okay, but for sure we need to accelerate the homework. Otherwise, I don't see us doing 6 homeworks this year. Okay, so next homework is due basically, you know. Okay, all right. Some logistics here. On Friday, we're not going to have recitation, but Suvik is going to be in his office in 311 Cushing. 311, I think it says F outside, 311F, okay, during the lecture time. And the purpose of the homework is for everybody to do it, even if we have to give you the solution. Okay? So you cannot leave basically the room on Friday without having the solution done. There is no such a thing, oh, it's a difficult problem, I will leave it for later. We want you to do it, even if that means you ask him for the solution. Okay? We want it done. On Monday, I'm away, and Suvik is going to give the recitation for homework 2 that we hope it will be posted this weekend. Okay? So there will be a recitation for homework 2 on Monday, and then I will take the lecture on Friday, basically. Thursday and Friday, I will give the lecture next week. Okay. So what we do today is we need to discuss, we need to go back to the elimination algorithm, which is sort of very trivial. But where we stopped was sort of to provide a graph theoretic approach to elimination. I mean, we said we eliminate nodes, you know, we sum over the potentials that depend on the variables we eliminate, but what is the right ordering, how we control the complexity of the algorithm, and how we do this purely using graph theoretic approaches, that has not been discussed. So let me, I'm going to summarize very briefly the algorithm so we remember what we're talking, okay? So the elimination algorithm basically has the following steps. The first step is to initialize. You have to choose some ordering where the query nodes, the ones that you want basically to compute, let's say, the marginal are the last, okay? So the ordering is such that XF, F is the query nodes, appears the last. And then you have to create a list of acting potentials, if you like, and because this is a direct graph, you go through each node in the graph and you place all the conditional probabilities that define basically altogether the factorization of the joint distribution. You put them on what's called the active list. Now, in addition to those, in the second step, when you call evidence, you also put in the active list these evidence functions, which were nothing else but delta functions that force this variable to take value 5, let's say. All right? So sort of, you don't really need to have it explicitly, but conceptually at least this needs to come somewhere. So if you want it just a formal presentation, basically you need to put this evidence functions, all right, in the active list in addition to these conditional potentials. Okay, and then following your elimination order, what you need to do is you have to go to every node xi following that order I, and you have to find all the potentials that depend on xi. All right, so basically this will be the evidence functions will be xi depending on its parents, the children depending on xi if xi is the parent, etc. Okay, so multiply all those together, sum on xi, and then form a new potential, which we call it Vxi, and then place this potential in the active list. And all the other potentials basically that you introduce here that involve xi will be removed from the active list. Okay, so you'll be substituting this with phi of xi. And the last step is basically if you want to normalize, you can do this by summing over all possible values of the query variables. All right. Now, to be able to introduce sort of a graph theoretic version of this algorithm, unfortunately, we have to discuss a little bit on how we do factorization in undirected graphs, which is actually my next lecture. So I'm going to be sort of a little bit ahead and then go backwards. All right? So you may think education is not the right thing to do, but in life, not everything is the right thing to do. All right? So doing some things out of order helps sometimes. Or if you hear some things twice in different order, that can be helpful as well. Okay, so let's see where the situation is. So we're going to discuss this elimination algorithm for undirected graphs. And the only thing that I want you to know, which will be actually our next lecture, there is no conditional probabilities in undirected graphs the way we had them in directed graphs. What you have is you have potential over a set of nodes. You have a product of potentials over a set of interconnected nodes, which we call them cliques. Okay? And those potentials are not really probability distributions. All right? Which means they don't normalize, or they don't have the physical meaning that the conditional distributions had in directed graphs. So in this undirected graph here, if you look for the number of cliques, the maximal cliques that somebody can have, is you can see x1, x2 is a clique. They're connected. x1, x3 is a clique. x3, x5 is a clique. x2, x5 and x6 is a clique. And x2 and x4 is a clique. Okay? x1, x2, x5, x3 is not a clique because x1 and x5 are not connected. Okay? So the maximal cliques are basically the ones that are listed here. The only thing I want you to know in the context of undirected graphs, basically the joint distribution of all the variables will be written as the product of some potentials that are defined using the variables over each clique. And we will not give you any specific details. What they are can be anything. The only constraint actually is that they are positive. So effectively when you multiply them, you get a probability distribution, which will not be normalized, but that's the only thing I want you to understand. So for example, if this is the same example we did earlier, but I am showing this for undirected graphs. If you want to find the joint of x1 and x6, where x6 is given, so that's an evidence node, what you need to do is you have to write the, you have to factorize the joint probability of all the variables and integrate everything out except x1 and x6. You'll have to integrate x2, x3, x4, x5, fix x6 with this evidence function to this x bar 6, and you notice instead of probabilities here, I have these potential functions. This is the way we define undirected graphs. Okay? And again, as I said, we will see this slowly in the following lecture that we'll start today, but I want you to see it now because I'm going to use some ideas from undirected graphs and redefine the elimination algorithm. So before we used to have conditional probabilities, but the rest, the operations on putting some of the summations inwards and in order of elimination of the nodes is the same for both sets of graphs. So for example, here, let's see, x6 is fixed to this value, okay? By the way, you notice when I use this delta function, the idea is when you use the delta function, you're going to have to sum on x6, right? So when you sum for all possible values of x6, only when you hit this x bar 6, this will be non-zero, so the rest is non-zero. So this summation sort of gives you only one value corresponding to this bar value there. Okay? So, so the summation in x6 is not shown on the second line. I already put the evidence here. And then I have to sum on x5, then on x4, on x3, and x2. And you notice here, I have potentials that involve the nodes 3, 5, all right, and 2, 5, and 6, 2, 5, and 6, okay? And I'm going to sum in 5, and I call this exactly as we did with directed graphs, phi of x5 subscript, and whatever nodes are left, let's see what is left there. x5 is summed up, x6 has some specific value, so it's of no interest, is x2 and x3, all right? So this doesn't involve any x4, so when I do the summation in x4 is exactly as before. I get another potential phi of x4 that depends only on x2. Then I have to sum this product in x3, and then I have to sum everything in x2. This is the normalization factor, right? So when we write it like that, the distribution is not normalized, so we have to put some normalization factor. And effectively, if you want to find the conditional, right, once you compute this, the conditional will be proportional to that, so you can normalize by summing this potential phi of x2 over all possible values of x1. Okay? So directed and undirected graphs don't really have any difference when it comes to the implementation of our standard elimination algorithm, but they will help us to do this sort of graphically. Okay? And it would be easier way not only to get the concept here right, but also to program this and implement it. Let me see if I had anything else to say here. Okay, so again, the only difference is not conditional probabilities, but potentials defined over maximal cliques. And I told you how many cliques you have here. 1, 2, 3, 4, and 5 cliques. Okay, this is what undirected graphs is. Okay. So we need a graphical way that somehow helps us to control the complexity of the eliminate algorithm. So we need to see how we're going to do this. And I'm going to start with this idea of what I call graph elimination, which is sort of the graph analog of the elimination algorithm we have seen. But I am going to pose this for undirected graphs for a reason, and then I will generalize to directed graphs. Okay? So let's see if this is fun. So here's a graph theoretic algorithm. So we have an elimination order I for a graph G, and the graph elimination algorithm, right? Graph elimination does the following. It says for every node in the elimination list, connect all of its neighbors, and then remove xi from the graph. Okay? And what is important here, and I put this in blue for a purpose, connect all the neighbors of xi. And the neighbors of a node in a direct graph is the graph neighbors. So that's a graph concept. It's not like you have arrows and you say the parents or the kids, and just the graph neighbors. Okay? So you connect all the neighbors, and then you remove xi from the graph. So let's see how this thing works graphically. So let's say this is the elimination order. We want to eliminate first x6, then x5, x4, x3, x2, and x1. So to eliminate x6, what do we need to do according to the elimination algorithm? Look at the neighbors. The neighbors are 2 and 5, and do what to the neighbors? Connect them. Then we eliminate x6. We get this. Then in our order, the next node is x5. Before we eliminate x5, we look at the neighbors, is x2 and x3. We connect them. And then with what we do to x5, eliminate. Then our next node is x4. The neighbor is x2. There is nothing, no need to put a link. So we eliminate x4, we get this. Then the next is x3, like this, and then x1. The key thing here is the following step, that somehow we connected the neighbors. All right? And where else did we connect the neighbors? So this was eliminated. And then this thing here that connected nodes 2 and 3. Okay? And again, the concept of the neighbors, right, is a graph theoretic concept in the context of undirected graphs. Now you notice that each time a node is eliminated, all of its neighbors are connected, forming a clique. That's what we call the elimination clique. So for example, here when I connect nodes 2 and 5, 2, 5, and 6 is a clique, fully connected set of nodes. Okay? When I go and I connect 2 and 3, 2, 3, and 5 is a clique. Okay? So that is the elimination clique, and it is very important. You can connect this back with the elimination algorithm we discussed before, but we will see this now in a graph theoretic fashion. So for example, in the cliques that we generated in the previous example is this clique 2, 5, and 6, and I call it 6 because it corresponds to node 6, right? This is the node that I'm going to eliminate from this clique, but this is the clique 2, 5, and 6, all right? And there is another clique that I generated, which is 2, 3, and 5, and I call it 5, C5, because I'm going to eliminate node 5, okay? So, key part of this graph elimination algorithm is that each time you remove a node, you record the collection of nodes that are the neighbors of Xi at that moment, including Xi itself. These are these maximal cliques that are formed during the elimination algorithm. Okay? All right. Now you, because the operations you're going to do, right, when you are going to eliminate a node, you are going to multiply, basically you're going to work with the potentials of these cliques. So the bigger the size of the clique, the more complex the algorithm will be, and that's why the largest clique that you come with defines the overall complexity of the algorithm. Okay? So in our case, basically the maximum size of the cliques is 3, so that will define the complexity of the algorithm. So let's say if each node takes k values, this will be k to the power 3. So k is what we saw in the earlier lecture as defined as the treewidth of the graph. Okay? Okay, so this defines basically the maximum size, the size of the maximum clique that you get when you implement this graph elimination algorithm. Okay? All right, so I'm looking here on the third bullet, right? So it says the elimination of the node has the effect of creating new dependencies between all pairs of neighbors, thus introducing a new clique in the graph. So the idea here is by saying connect the neighbors of X6, somehow nodes 2 and 5 become now dependent. And in normal circumstances, you wouldn't be able to see and say, there is a relation of nodes 2 and 5, right? I'm sorry, yeah, nodes 2 and 5. I mean, they're on the other side of this graph, but somehow if you're going to eliminate this X6, you introduce these dependencies between nodes 2 and 5, and we will see, if you don't do this step, when we work with directed graphs, basically you will not be able to model this correctly, okay? So in this particular case, you notice you form lots of triangulars, right? And that's why this process is called triangulation of the graph. All right. So let's see if this simple algorithm for an undirected graph, where we connect, in the order of elimination, we connect the neighbors of the node to be eliminated, forming these cliques. Let's see how this can be extended to a directed graph. So the first thing you need to do is basically eventually you're going to need to transform your directed graph to an undirected graph. But notice here, before you say, okay, transform it to an undirected graph and then apply the undirected graph elimination algorithm, then is an intermediate step, an previous step that's extremely important. It says moralize the graph first and then transform it to an undirected graph. And that's sort of a very tricky concept. If you miss the step, basically this algorithm will not work. So the idea here is not simply to transform it to an undirected graph, but you have to moralize it. And remind me, what's moralization here? connecting the parents basically. Okay, so the idea here is, for example, you need to connect the parents, let's say, of 6, which is 2 and 5, and then transform this to an undirected graph. The next few slides basically they show pictorially why if you don't do this step you would be messing things up. But can anybody basically just start thinking why that step is essential? Well, but you remember in the undirected graph, you also connect the neighbors, right? So somebody will say, when let's say I eliminate x6, 2 and 5 will be neighbors. I'm going to connect them. So there is the moralization. So I took care of it. So why do I need to moralize? What I'm saying is, it seems like in the first loop that because here we connect the neighbors, that maybe this does already the moralization. Does it? I mean, let's not go to the next graph, right? Let's start just imagining things, and then we can bypass many of the following slides. So let's say we make this an undirected graph, all right? Okay. So we will connect the neighbors. This is okay. So in this case, this is the moralized. Okay, this will not work. My graph. Okay. So let's see. Here's the example. If I eliminate x6 the way we did it before, there's not going to be any issue, right? So let me do the following. Rather than eliminating x6, because there we will not be able to, what difference the moralization does, let's say we eliminate x5 first, right? So let me go back to this slide and eliminate x5. And let's say we don't do any moralization. So if you don't do moralization and you transform this to, to an undirected graph, what is the first thing you're going to do on this graph? So there's no moralization here, right? So if I eliminate x5, what needs to happen in the undirected graph algorithm? What are the neighbors of 5? So let me show you the calculation, right? This is the undirected graph. So if I'm going to eliminate x5, what we need to do is we need to sum on x5 the following conditional distributions: x5 given x3, all right, and x6 given x2 and x5. We agree? This is from the directed graph. So basically, one way or another, this is the calculation that we need to do. And when you look at this calculation with x5 integrated out, we now get dependencies between which nodes? x2, x3, and x6. So let me see this. x2, x3, and x6. Is that dependency going to be there when we use just the undirected graph elimination algorithm without moralization? So again, we have a dependency between x2, x3, and x6. x2, x3, and x6. What is going to be missing when I apply the undirected graph elimination algorithm? So I need a dependency between x2, x3, and x6. So if you do this in the undirected graph without the moralization step, and you get rid of x5 first, what are you going to do in the graph? What link is going to be introduced? You remember in the eliminate algorithm, we need to connect the neighbors, right? And what are the neighbors of 5? 3 and 6. So what is going to be missing from the graph that somehow is not going to account for the dependency implied here? X2 and X3. So the link between X2 and X3 is going to be missing. It's not going to be there. Okay? On the other hand, if you normalize the parents of X6, what do? You link X2 and X5. All right? Is now, can you see if you eliminate X5, its neighbors become what nodes? In the undirected graph now, so you moralize, you're going to put this link from 3 to 5, all right? Now, if you're going to eliminate 5, the undirected graph algorithm says you need to connect the neighbors, and the neighbors of 5 now are going to be which ones? 2 and 3, and that's how you get the link of 2 and 3. In other ways, the moralization comes from X6, right? And you think it's not going to be relevant there, but now there is a dependency that you need to introduce between X2 and X3 that you see here that you're going to be missing because you didn't moralize the parents of X6. Okay? So the graph by the way, if you do this and you eliminate first X6, that's what I was asking initially, obviously you're not going to have a problem with the algorithm, but if you want to eliminate X5 first, that's when the problem appears. So here is the algorithm. You need to moralize the graph and then apply this undirected graph eliminate algorithm. So moralize it, transform it to an undirected graph, and apply this algorithm that is fully basically graph theoretic. All right. And again, this is how the algorithm is working in action. For example, if let's say the elimination is you eliminate, this was the dark lines of the original graph. You marry this. So this dotted line comes from moralization. And this line comes from where? This is because, you marry the parents of X6. And this line comes because what? When you're ready to eliminate X5, you need to connect its neighbors that they are 2 and 3. So two different origins. One is the moralization, the other one is coming by connecting. So one comes basically from this part of the algorithm, the other one comes from the undirected graph elimination. All right. The rest is really nothing. We already have seen it. Okay. So I'm going to stop there, and then I'm going to switch lecture. And I'm going to go to, only if my computer, do you see a mouse on the screen? Huh? So what do I supposed to do? Okay, let me remove this thing out first. Now people lost us on the computer screen. So we're going to basically see now slowly this concept of factorization of distributions in undirected graphs. Okay? And actually, I'm going to come back to this topic sort of in a more rigorous language, maybe in 4 or 5 lectures. Okay? So, but right now we're going to do sort of an intermediate, easygoing presentation of undirected graphs. And maybe next Thursday we'll discuss a little bit about what's called factor graphs. All right, so we have seen this in more detail. We just discussed about undirected graphs. Another name for undirected graphs is Markov random fields. For those in physics, engineering, etc., mostly you'll be interested in this type of models. People, for example, in social networks, in problems that there is causal relations, they are interested in Bayesian networks. But actually, most algorithms that if you want to operate on this, you will transform it to some other form, most probably an undirected graph or a factor graph. Okay, so it's not like we're going to learn 10 different techniques for each graph, but I'm just saying this is the standard way of doing things, let's say in engineering, modeling random properties and things like that. This is more in when you have causality relations. Okay, we mentioned one example that we're going to come back now to it. Okay, so Markov random fields basically, are models. So we have nodes exactly as before, that they are random variables. We have edges that describe basically independence relations, and there is no asymmetry that has to do with direction of arrows. So there is no such a thing. I'm your parent. Here, everybody is the parent. So the relation between A and C is equivalent. Okay, there is no directionality here. And it comes up that the independence relations, this is very important on undirected graphs, they're basically graph separation ideas. So what do I mean with that? Here is one relation. I say that A and B are independent given C and D. Okay? So what happens is, so you condition on C and D, and I claim that A is independent of B because every path from A to B has to pass through C and D. So if I given C and D, the path is blocked in a completely graph theoretic way. In other words, there is no path from A to B that doesn't pass through C, the union of C and D. Okay? It's a fully theoretic, graph theoretic algorithm, right? So you don't have this explain away thing we had with the fork independence that we show in directed graphical models. So here, if you apply the Bayes ball algorithm and you have to pass through a path of nodes that are described, basically that immediately defines the conditional independence relations for this graph. All right, a very simple calculation. If you have m random variables, okay, and let's see, what I'm doing is I'm computing all possible ways of coming up with relations, let's say here, between three random variables. Okay? So in this case, the three random variables are fully independent. All right, here there's one connection, other connection, etc. And the total number of, if I have m random variables, and they're binary, let's say in this case, no, actually not binary. This 2 here stands for what? This is the total number of undirected graphs. If I have m random variables and I claim it's 2 to the power m minus 1 over 2, the 2 stands for what? I mean, if I have 2 nodes, these nodes are connected or they're not connected. That's where the 2 comes, okay? So the total number of graphs that you can get, undirected graphs, on a set of m random variables is 2 to the power m times m minus 1 over 2. M is because you have m nodes, and every node can be connected with the other m minus 1 node, and 2 because there is no directionality, so you have to not to double count basically the number of graphs. Now, which graph basically represents your problem based on a realization of the random variables? That's a graph structure optimization problem, and we'll come back to it way later in the course. All right, conditional independence relations in undirected graphs is what I described before. Extremely simple. There is no, you don't need to remember the rules, with head-to-head and heads and tails and all of these things that we did for directed graphs. This is independent of that given xb when every path from this set of nodes to this set of nodes has to pass through the xb nodes. Okay? So basically the concept of conditional independence becomes a graph theoretic concept, okay? It has nothing to do with any particular details that we have seen for directed graphs. Is this equation correct. I want you to look at this equation and tell me, so basically what I say here, we have two nodes on the graph, and I'm assuming that they're not connected via net. So a node I here, a node J, not connected. Is this equation based on my graph, this conditional independence condition? Is this correct? If I and J are not connected, right, every path from I to J has to go through what? I is here, J is there, they're not connected. The only way to go is through the other node. Right? You have to go through whatever the other nodes, and immediately we know if the other nodes are given, like we condition there, then given this, xi and xj have to be independent. You see that? I mean, before we said, right, that this is independent of that if given xb, if every path from here to there has to pass through xb, because xb will block it. So here, if I and j don't form an edge, I can claim that they are conditionally independent given the rest of the nodes, because the only way I can go from I to j is through the rest of the nodes which block that path. Okay? So the idea here is I'm writing this as a sort of a generic, if you like, a generic conditional independence relation, but I want basically to motivate the concept that the joint probability distribution can be written as a product of potentials where each of them is defined over a clique. Okay? So this relation of potentials defined over the clique is sort of a way to implicitly enforce the independence relation that we see up there. Okay? So let's see what, I'm not going to go on this thing because we already have seen it. Okay? So let's see an example of with 4 nodes and see what cliques we have here. So these are the edges of the graph. So the only connection I don't have is between x1 and x4. Okay? So there are, this is a clique, all right, one clique. X1, X2, X3 is another clique. X2, X3, X4 is another clique, right? And so the maximal cliques basically here of size 3. So how do we write the joint distribution? We write it as product of potentials defined over each maximal clique. Okay. Actually, what you should do, right, as a sort of a little exercise, and maybe Shuvik can give you a little homework problem, is start with this, all right, with some simple setup, and then basically show the independence, the conditional independence relation that I mentioned before. That if somehow these nodes come over maximal cliques, right, obviously they don't overlap. And that enforces directly these conditional independence relations that we mentioned before. Okay? So, Z is the normalization factor because these potentials are not probabilities, right? They're just, functions. But in some sense, even though they're not probabilities, they sort of the values that they take express how related are pairs or triplets, let's say, of variables, right? Depending how many variables you have on this set. So they are not probabilities, but they actually capture the way the variables are correlated in the graph in an implicit manner. Okay, so in this particular problem, all right, so what I have done is there is the 4 nodes don't form a clique because W and Z is not connected. So if I have these 4 variables, I can write the joint probability distribution as the probability of 2 maximal cliques that are one X, Y, and Z, and another one W, Y, and X. Okay? Often, all right, this decomposition that we see there is not unique. All right, so sometimes, you can manipulate things differently and come up with some other ways to express this clique potential. So this decomposition doesn't have to be unique. But right now, that's not an issue, because at the end of the day, you're interested only in the joint distribution. So let's do one example, simple 3 nodes, okay? And see how we can represent this in terms of potentials, okay? So what I'm going to do is, I'm going to use, there is only one graph separation and conditional independence relation here that says that given y, x and z are independent, okay? So we're going to try to enforce this and see that this expression actually leads to decomposition over cliques of the joint distribution. So what you see here is p of x and y and z is equal to that. So this equation that you see in the middle is just the product rule. There's nothing assumption there. But I simplify and I say that p of z given x and y is p of z given y. What have I used to do this? I use the independence relation, okay? All right, so effectively, what I can do is I can combine those things together, and this becomes the joint of x and y, and this becomes, is the condition of z given y. So I can call really this my xy potential, because that's one clique, and I can call this my yz potential that comes from this clique. Interestingly note, there is no way in general to write this. I mean, this is a trivial example, but you cannot write this, you cannot factorize this distribution in terms of, let's say, conditional distributions alone or joint distributions alone. It's just not going to happen, all right? So in this case, you get one joint distribution as one potential, another one a conditional as the other potential. And I'm also, I mentioned that this decomposition is not unique. If you follow the algebra, I'm not going to go through this, it's just combining the p of y with p of z comma y. I can write this in another factorization, where the yz potential becomes the joint of y and z, and the xy potential becomes the conditional of x given y. So it's not unique. Okay? And as I said, it doesn't really matter. It's not like this is better than that. You know, they will do the same idea. And actually, we will not even bother to model this and say it is a joint or it's a condition. No, it's some potential, another potential defined over the two cliques, and that will do the job. All right, so this is the most important theorem, basically, and has 2 or 3 versions. Fundamental theorem coming from statistical mechanics, really. The Hammersley-Clifford Theorem, any distribution that's consistent with an undirected graph. And consistent means it satisfies this conditional independence relations implied by the graph. It has a joint distribution that factorizes over maximal cliques and looks like this. Okay? These functions at this point are any positive value functions of the variables in each clique. Okay? So if you think, I mean, this is sort of not a trivial theorem, even though the proof is 2 lines. I mean, there's really nothing to prove there, but it's so fundamental. It says any distribution that satisfies this conditional independence relations implied by completely graph theoretic arguments has to factorize as the product of potentials, each potential defined over a maximal clique. Okay? So that's the Hammersley-Clifford Theorem. All right? And I mean, this is basically another version of the same theorem. It says if U1 is the family of distributions that factorizes like this, and U2 is the family of distributions that satisfies all conditional independence relations, then U1 equal to U2. Okay? So if you set down and you write all possible distributions that account for all the independence relations implied by this undirected graph, and then you take all distributions that are factorizing like that, then the 2 things are the same. Let me see if I'm going to do this. So let me do an example, okay, and tell you in which form these potentials are coming usually in practice. So consider that these are rooms, for example, in this building, right? And each of the nodes is a variable that measures, let's say, if the temperature, if it is warm or cold, all right? The heating system is on or off. So we take that this variable xi here is a binary, +1, -1, just to make life easy. Obviously, if this room is cold, right, you expect the nearby room to be cold, all right, because they communicate through the wall. So there is some correlation, and that correlation sort of we're going to try to capture it with a potential that is defined over the clique xi and xj. And I am sure, you know, in your elementary courses, when you play with this type of models, you always say, oh, I'm going to take nearest neighbors for interactions, you know. So in this graph, obviously, what's the size of the biggest cliques on this graph, the way that you see it? Is it 4? Is the size of this cliques 4? And the reason, again, it's not, no, is because, remember, a clique is, you know, a maximal clique is every node has to be interconnected. It cannot be 4 because this node and that node are not connected. So what's the maximum size? Is it 3? It's 2, okay? So it's 2. So we're going to have to work here with potentials that involve basically 2 variables that they are sort of neighbors, okay? So let me write directly the joint probability distribution, and I will introduce some parameters. You know, theta is let's say, whatever parameters define the potential are unknown in general, all right? But I'm going to write this as a product of potentials. And you remember the potentials need to be positive because when you put them together, you need to get the probability distribution. And an easy way to make them positive is to write them as e to some power, okay? This is sort of very typical of Boltzmann type of distribution. So here I am writing each potential as e to theta ij that connects nodes xi and xj. And so my potential is really not theta ij, is e to the theta ij, where theta ij is some function. Because that way the function can be positive or negative, but e to the theta ij will always be positive. I'm just reformulating basically so I don't have to worry about something being negative, okay? Another advantage is if you write this as product of these exponential functions, when you multiply them together, you know, based on the theorem we discussed before, you're going to get e to the sum of the theta ij's defined over all the edges of the graph. Okay? All right? And z is a normalization factor, which means this e to the summation of this, you're going to have to sum for all possible values of xi and xj. All right? And we're going to come back to this, and hopefully you may have to do a homework or so, because this term is where all the physics is coming. So if you want to do statistical mechanics or compute interesting properties, you really, everything has to go through this normalization factor that sort of corresponds to free energy for the system, okay? And you notice it's complicated because it's summation of the e to the summation. All right, so how you exactly do this is to be seen. All right. So this is a Boltzmann-like distribution, okay? And there's nothing here. Now, so in the previous graph, right, in the example, we started with a graph and we wrote down the factorization of the distribution over the graph. Now, suppose we go the other way around, and somebody gives you a factorization defined over a set of nodes. How do you specify an undirected graph, basically, that obeys to that factorization? The other problem, basically. So if I write that p of x is some function of x1, x2, and x5 times another function of x4, x3, and x25, how do you make a graph? Well, the idea is very simple, right? They have to be nodes corresponding to maximal cliques. So what you need to do is, you need to take all the nodes defined inside these potentials and connect them. And when you finish, that's basically your undirected graph. Okay? There is no other way around, because that's the only way that will allow you to have a factorization that basically looks in this form. All right? So this comes a little bit off because it has to do with the independent relations, but I don't have to tell you much about the biggest ball algorithm, right? Because if you want to show that x1 and x is independent of x5 given x2 and x4, the only thing you have to do is take a path from 1 to 5, and if it has to go through 2 and 4, then the path is blocked, right? So you can use purely basically reachability conditions. If you can reach one set of nodes from one set of nodes another set by bypassing the evidence, then basically the conditional independence relation will not be valid. Okay. So what's the meaning of these potential tables, right? So if, before we had conditional distributions, now, if I write, this is the same example that we had before. If I write this in terms of potentials, these potentials of two nodes, two variables, and then 3, these are not probabilities, okay? And they express correlations between variables. So at some point you see let's say if these are discrete variables and you see an element there that is very small, means the particular set of variables are not correlated with each other. But let me tell you what potentially it's something computationally you need to worry. Because these factors are not normalized, you may have a problem when you do computation and inference, let's say, of parameters, because maybe this potential here is way of much higher values than that potential there. That doesn't imply that the variables x1 and x2 basically dominate the distribution. Simply this happens because you haven't normalized it. So you need to be careful when you do inference, because these terms may be completely unbalanced in the calculation because they are not probabilities. Okay? In some sense this can be a problem, depending what your task is. Some other occasions you may want to take advantage of that. All right. So the most famous problem that fits in this concept of undirected graphical models is the Ising model. For those who have taken elementary courses in physics, this is the spin model, where the variables basically are plus minus 1. So this is your typical magnetism problem, but actually, as trivial as this problem looks like, all right, is also one of the most difficult problems to do, especially in 2 and 3 dimensions. Anybody that thinks this is a toy problem, there are textbooks basically written of hundreds of pages that are discussed about this problem, and it is sort of a good test case for checking the algorithms if actually they work, okay? And so let's discuss it, because it has to do a lot with statistical mechanics. This is in 1D. Its variable can be plus minus 1. And what you need to capture of the Ising model is you need to capture sort of correlations between neighbors. So if this is plus 1, in physics you say spin up, for example, in quantum mechanics. So if this is plus 1, then the neighbors tend to be plus 1. So the corresponding values then of the potential for getting, if this is plus 1, there's higher chance of getting this plus 1 and higher chance of getting this plus 1. And this table is supposed sort of to represent that, not in the context of probabilities, but certainly in the context, in the context of the potential. So you can see here, for example, if this is -1, the probability of xi minus 1 being -1, I mean, it's not the probability, the value of the potential is much higher than the probability than the value of xi minus 1 to be 0.2. Okay? Again, I have to correct myself. These are not probabilities. And you notice they don't sum up basically in any direction you see them to 1. So you write this joint distribution as the product of potential functions of the form e to the -8. Okay? This product will lead to a summation of the potentials, and this is basically your Hamiltonian for the system. This is the energy of the system, which is the summation of the energies over each clique. So in lots of problems in undirected graphical models, not just in the Ising model, rather than actually starting with potentials, you know what you start is with an energy function, and then e to the minus that basically will give you the potential. All right, so lots of times you will see people postulating directly the energy over cliques, all right, and the corresponding distribution will be a Boltzmann distribution or a Gibbs distribution, e to the minus 8, okay? And if you want to make it fancy, you can introduce temperature effects and things like that, but of no interest right now. Okay, so this is corresponds to the Boltzmann distribution. All right. What's the Markov blanket? Can you remind me what's the Markov blanket in general for a directed graph, for example? What was the definition? So it was the parents and the co-parents, and the idea was, given the Markov blanket, basically the nodes independent of anything else in the graph. All right. So in undirected graphs, if you want to think what the Markov blanket is, it is extremely trivial because the Markov blanket is really the neighbors of the node. Because if you given the neighbors, there's no way to go anywhere else because all paths will be blocked. Okay? So the Markov blanket for an undirected graph is the neighbors of the nodes. Okay? So if, when we were discussing about directed graphs, we posed some sort of trivial inference problem. So if you want, for example, so you have a lot of nodes here. Right? Let's say this is the problem with X being hot or cold, different rooms, and and these are the temperatures in each room. If you want to find, given some evidence, you want to find this conditional distribution where the rest of the variables xi's are eliminated. Basically what you need to do is this, you can write the numerator like that, and the denominator, these things have overall possible values of xk, that in this case take values -1 and 1, and the way you handle evidence is sort of identical with the way we handle evidence in directed graphs. So you can, so on the denominator here you have the joint of xk with the evidence xi, xj. So effectively, if this expression is written correctly, this is a summation of over all variables except xk. But notice also I multiply the joint distribution with the evidence functions to force the variables xi and xj to take these hat values. Okay? So there's nothing, again, different from before. The only difference is that this is written in terms of these potentials rather than conditional distributions. So the algebra is basically sort of identical. All right. How do we transform now? We did lots of things about directed graphs. If you don't want to work with directed graphs, how do you transform them to undirected graphs? So let's look at for the directed graph, let's look at the joint probability distribution. So x1, x2, x3 have no parents. x4 has 3 parents, so we get something like that. All right. So what is, based on this, and thinking what the undirected graph is going to look like, what is the maximum clique that I need to have in the problem to represent correctly that factorization? What is the maximum clique I need to have to represent this term? Huh? But this has x1, x2, x3, and x4. Right? Because x4 depends on x1, x2, x3, so I have a term here that involves basically 4 variables. So what is the maximum clique that I expect to see on the equivalent undirected graph? 4. But how can you get 4 from this graph? The only way you can get 4 is moralization. All right? So basically you have to marry these parents, you have to marry these parents, you have to marry these parents, and this basically will give you a clique that is a maximum clique that's of order 4. So actually in this particular case, right, I can write this as only one potential, because really there's only one maximal clique that involves all 4 nodes. I can write this as psi1 of x1, x2, x3, and x4. Okay? Now keep in mind, if you try to write this sort of with lower order terms, it sort of will be a model approximation, right? So you will get some results, but in reality you will never be able to exactly model a distribution that factorizes this way. The only way you can do this is by having a maximal clique that has all 4 nodes, and this maximal clique can only be obtained if you moralize the directed graph. Okay? I think I'm going to go back to show you some cases of directed graphs that there is no way you can come up with an equivalent undirected graph, but right now, for this problem, you just moralize the parents and the relatives. Okay? So, so here's another example. If you have this directed graph, P of x1 has no parents, P of x2 given x1, x4, P of x3 has no parents, and then x4 given x2 and x3. Okay? So, so you notice here, you have variables 2, 3, and 4. All right, 2, 3, and 4. So immediately I see there a clique that involves 2, 3, and 4. And obviously to get 2, 3, and 4, you have to moralize, you have to marry the parents 2 and 3. And this is the line here. But also notice, because if I say I'm going to have a potential 2, 3, and 4, in that potential I can take actually this probability of x3 and make it part of that potential. All right, so if you want to go from the left to the right, I can combine P of x3 with the probability of x4, x2, x3, and define this potential. And again, because x1 and x2 is a clique of 2 nodes, I can put these things together as another potential psi1, 2 of x1 and x2. So again, you have a potential with 2 nodes and another potential with 3 nodes. And do you have a problem that one node belongs in one potential and another? Is that an issue? I mean, obviously you expect, right? I mean, if you think if these cliques account for the way variables are correlated, and you take a bunch of them here and a bunch of them neighbors, obviously they're going to be sharing some nodes. If they don't share, basically there's no point of doing any methodology, because the problem becomes trivial. So the fact that there is no 2 here is not an issue. You know, this is typical in this sort of problems. So let's look actually again for converting it directly to an undirected graph. So what I have here, I have 7 nodes. This is the factorization for the directed graph. And what I have done is, these conditional distributions I have written down as a product of joint distributions divided by marginals. And if you look carefully at these expressions, you will see that on the numerator I have products over cliques, all right, divided over products of clique intersections. You see here, there is x1, x3, all right? x2, x3. So this 3 is basically the intersection of the two cliques. Of course, there is 3 and 4. There is another intersection there. And similarly, for the cliques for 5, for 6, for 7, right? You have these intersections. Later on, when we develop algorithms basically for inference on general graphs, we will try to take advantage on how these cliques communicate with each other. So this is sort of this idea will be extended. All right. So this is a trivial example. I don't, it's a Markov chain basically. So again, I combine this to one potential and each of the other conditional distributions to other potentials. Okay, so nothing fancy. So here you can remove all the errors and make basically this graph to have the same identical independence relations as the direct graph that you see on the top. All right. So what I have here is I have an undirected tree, a directed tree, and a poly tree. Okay, and so can you remind me what's the definition of an undirected tree? Obviously, it's undirected. What makes an undirected graph a tree? It says there is a single path between any pair of nodes. To go from here to there, this is the only path. To go from here to there, there's only one path. Okay? What's a directed tree? So in a directed tree, there is a root node, let's say this node here, and every other node has how many parents? Only one. So what's the relation of a directed tree, you think, an undirected tree? You remember that to transform, right, a directed tree to undirected tree, we have to do first what process? Moralization. So what happens if I do moralization in a directed tree? Huh? Nothing happens. Okay? So basically, because there's no moralization, nothing happens. But in a poly tree is like a directed tree, but nodes can have more than one parent. So what will happen when I transform a poly tree to an undirected tree? So for example, to make this an undirected, well, if I can make it this is a poly tree, right? So if I wanted to make it an undirected graph, what is going to happen here? You will connect the parents, and if you connect the parents, what is going to happen? Is that becoming is that a tree? No. So that can be troubling, because inference, as we will see in trees, is very easy. All right, we'll spend one lecture or two. So if your problem is a directed tree, easily you can transform it to an undirected tree and do everything extremely cheaply. If it is a poly tree, you can, because you moralize, you get loops, and that is a problem. And there is a way to get around this if you actually transform the poly tree not to an undirected graph, but to a factor graph, which is another type of graph that, if we have a few minutes, I'm going to show you how it looks like. Okay? And something that is common sense, right? If you have an undirected tree, I don't see, by the way, a reason why you'd be interested to make it a directed tree. But if you read here, it says from an undirected graph, we can produce n directed graphs, one for each selection of the root node. So the idea here is, if I give you an undirected graph, and for whatever weird reason you want to make it a direct graph, you're going to have to say, okay, let me select this to be the root node, and start pointing arrows away from the root node. So we'll go this way, and this way, and then that way, and that way. But you can start with any node, so you can produce actually n-directed graphs that they are not necessarily equivalent. Okay? I don't see any reason why anybody will be interested to transform an undirected graph to a directed graph, all right? Unless, of course, you're trying to learn the causal relationship model and given data, then I can see a reason. And in that case, the problem will become a graph selection problem because you'll be asking which of these graphs better represents the data that I collected, and that's an interesting problem. All right. Okay, so let me, 4 minutes, let me do a very sort of standard problem. Every textbook in machine learning and graphical models has this problem. And this is a problem related to image denoising. So you can think xi representing pixel values, so that can be black or white, let's say, binary, okay, and of an image. And yi are what you measure, which are noisy versions of xi. All right? So you have an image, but you only have some noisy version of it that is represented by y, okay? Obviously, you know, if you have an image, if xi is black, you expect the neighbors to be black, right? So the cliques that express sort of these sort of correlations will be the clique that you see here, okay? And obviously, xy and yi are correlated because I envision yi to be a noisy version of xi. So if you want to write the joint distribution of x and y, of all the x pixels and y pixels from this image, basically you have a product of potentials that account for the correlations of xi and xj, all right? And then a product of potentials defined over the cliques xi and y, which are these potentials that you see in here. All right? So a good way, again, is to pose these problems rather than writing these potentials explicitly, is to point them, to write them down in terms of the energy of the system. And you remember that potential terms are e to the minus the energy. So the energy here, it will be defined by these local correlations on that I indicated before between xi and xj and xi and yi. So those are the two terms defined over the two cliques. But also notice there is a very common term that involves summation of all the xi's. Okay? And usually in physics, right, the term is used to, you know, control, if you like, the average black pixels in the model, like, or the concentration, or something like that, is used sort of for regularizing reasons, all right? But you can think, of course, xi alone is not the maximal clique, right? But you can think each node is a sub-clique, so you throw an extra term there, okay? So the parameters here, beta and eta and h, are unknown. So, you know, if somebody can pose the problem using the data y to go and compute those parameters, but right now, let's say you fix them and you don't, you know, you don't worry about them. All right. So so here you notice that xi really relates only with xj, its neighbor, and xi and y they relate together. So I'm not saying that xi is related to that, but if you try to write the conditional distribution and you say, if I have observed the whole image, the noisy version y, can I compute x, what x is? Notice now all the x's are coupled with, the x's are coupled with all the y's in both potential terms. All right, so when we try to write this conditional, you know, these potentials here involve all the y's, right? And this makes the problem a little bit sort of tricky on the way you're going to implement it. All right, so let me show you sort of a trivial algorithm to do this in a code of 5 lines. So let's say that, can we make this a homework actually? All right, just make this a homework, because it's 5 lines. Well, I mean, this I have to motivate Suvik to write the right homeworks. So if you keep notes, how many of those become homeworks? Okay? So here's the idea. This is the original image, and you notice it's very clean. And let's say you take the original image and you perturb, from black to white to black, 10% of the pixels. So this is your noisy image, and you want from this noisy image to go back and compute the x's, all right? So the x given the y. All right, so the algorithm actually that is implemented, the elementary algorithm, because we haven't done anything, what you do is you go through a loop of the nodes, all right? And you remember, what you need is, you need to find the probability of x given y that takes the maximum possible value. I mean, that's what, so when you do this, right, you're asking, if you want to compute, let's say this, you say, so you have x given y, you want to find the x that maximizes that posterior of x given y. So what you do is, maximizing the probability is the same as minimizing the energy of the system. So what you do is you take a pixel, if it is black, you compute the energy, you say, okay, now let me make it white. Does the energy goes down? If it goes down, then you keep it white. And you do a few loops through the pixels, all right, by perturbing them up and down, all right, until you reach a minimal energy. You can do this, with